Welcome to the Science Fusion presentation on the elevated mix layer and its association with severe convective storms in the northeastern United States. I'm Pete Banakis, Science and Operations Officer at the National Weather Service in Burlington, and I will be leading this presentation. Here are the learning objectives for this presentation. First, we want to know what the elevated mix layer is and to be able to describe how the EML affects the convective storm environment. Next, we will describe the processes involved in EML formation, transport, and evolution. We want to examine the synoptic climatology of the EML incursion into the northeastern United States, which is relatively rare. As such, we want to understand the synoptic setting that is favorable for transport of the EML into the Northeast. We'll use a severe weather case study to tie everything together. And lastly, we'll provide some tools and guidelines for recognizing the EML in real-time data. The generation of an elevated mix layer, or EML for short, all begins with a surface-based mix layer over elevated terrain in dry continental air masses. Once the snow melts in late winter and early spring, and as the sun angle increases, insulational heating becomes quite strong across the elevated terrain of the Intermountain West, with the elevated terrain is both wide and expansive. The air masses are typically quite dry in this region, yielding very deep daytime boundary layers during the spring and summer, sometimes with dry adiabatic lapse rates up through 500 millibars or even higher. Once formed, these steep dry adiabatic lapse rates are pushed around by the prevailing flow and often emerge into the Great Plains, juxtaposed over a lower elevation, local boundary layer that can be quite moist. In this particular example, the deeply mixed daytime boundary layer at Albuquerque, New Mexico, is advected by the prevailing flow east-northeastward and is apparent in the mid-levels of a sounding at Dodge City, Kansas, several hundred kilometers downstream. At Dodge City, these steep mid-level lapse rates are removed from the surface and distinct from the local boundary layer, and we refer to this as an elevated mix layer. The elevated mix layer is an important factor in the formation of loaded gun soundings in the Great Plains, which were documented by Fawbush and Miller dating back to their paper published in the Bulletin of the American Meteorological Society in 1954. The capping inversion evident on the Dodge City sounding helps in the buildup of convective available potential energy, or CAPE. If this capping inversion is weakened and overcome at a later time, the dry adiabatic lapse rates in the mid-troposphere bring the potential for very large buoyant accelerations and the potential for severe convective storms. So environmental lapse rates can be advected by the prevailing flow in the atmosphere, and we'll be elaborating on this throughout the presentation. In this graphic, note the almost perfect overlay of the soundings from Albuquerque and Dodge City in the 700 to 400 millibar layer with a uniform potential temperature and nearly dry adiabatic lapse rates. It's apparent that this mid-level air mass at Dodge City was sourced from the mountainous terrain upstream. In addition to the steep lapse rates, the EML is a very dry layer, a function of the source region of this air mass. The relative humidity increases with height in the elevated mix layer, sometimes sufficiently to produce altocumulus castellanus clouds near the top of the EML associated with instability and mid-level saturation. When other cloud types are absent, this can be a visual clue about the presence of an EML. The local boundary layer is moist at Dodge City and highlighted in green. In between the local boundary layer and the EML, we have a transition or interface layer, typically marked by a capping inversion or simply the cap. As we know, the cap will act to preclude surface-based convection until such time that it is overcome, usually through a combination of strong surface-based heating and vertical stretching through large-scale processes inducing lift. These things will weaken the cap and the associated convective inhibition. In other situations, especially in the absence of mesoscale or synoptic vertical motion, the cap will hold firm and nothing much interesting happens. We'll explore the other types of processes that can modify lapse rates as we go along in this talk. So why is the EML favorable for severe thunderstorms? First, you have the potential for strong buoyant partial accelerations in both updrafts and downdrafts. Second, prior to thunderstorm development, the strong capping inversion allows for the buildup of large CAPE before convective initiation, generally yielding stronger convective storms once the CAPE is ultimately released. Third, the low mid-level relative humidity contributes to greater potential evaporation and downdraft strength once thunderstorms are present. I want to say here that the EML doesn't necessarily say anything about the expected convective mode. That will depend on the geometry of the forcing for ascent and other factors such as cold pool interactions and the nature of the wind and shear profiles relative to boundaries, just to name a few examples. There are documented cases of both tornadic supercells and deratios within EML environments. Some other facts of note, again, recognition of the importance of the EML dates back to the description of the loaded gun, Miller Type 1 sounding with steep mid-level lapse rates by Fawbush and Miller in the early 1950s. The EML was first discussed as a physical feature by David Ludlum and Toby Carlson during the 1960s. And lastly, the EML is not a feature unique to the United States. It is common in other parts of the world near and downstream of mountain ranges. In their 1997 paper, Lang and Fritsch investigated the global population of mesoscale convective complexes. MCCs with the highest frequency are shown in the dark shaded areas on the map and are prevalent downwind of major mountain ranges and escarpments around the world in both tropics and mid-latitudes. This is partly a function of having frequently available steep mid-level lapse rates within plumes of elevated mixed layer air to help maintain deep convection, especially during nighttime hours. Some noteworthy locations for MCCs include areas east of the Rockies, off the Mexican Plateau into the Gulf of California, east of the Andes Mountains, east of the Alps, near the Indian Plateau and the Himalayan Mountains, and east of the Drakensberg Escarpment of southern Africa. It turns out that elevated mixed layers are generally wiped out before advecting very far from their source region. An ERA5-based EML climatology by Andrews and co-authors in 2024 showed that EML frequency is highest over the central and southern plains and east of the Mexican Plateau in the spring, and highest across the central and northern high plains during the summer months. When the sun angle is relatively low and higher elevations of the western United States may become snow-covered, EML frequency drops in the latter half of the fall and is limited to the southern latitudes during the months of December, January, and February. Note that the frequency of EMLs drops off steadily to the east of the Great Plains, with generally just a few EML days per year along the east coast of the United States, including the Northeast. So this leads to a couple of obvious questions. The first is, what are the physical processes that act to destroy the elevated mixed layer to make the climatology look the way it does in the east-west direction? And secondly, what processes and synoptic regimes allow for a longer range transport of an elevated mixed layer, such as those rare occasions when the EML reaches the northeast? We'll answer those questions next. In a paper by Banakis and Exter in 2010, a lapse rate tendency equation is shown that describes 5 atmospheric processes that can modify lapse rate. We'll first note that lapse rate, denoted by gamma, is defined as the negative of the vertical temperature change with respect to height, such that the normal decrease of temperature with height in the troposphere yields a positive value of lapse rate. You can read the paper for the equation itself, but it's probably more instructive for the purposes of this presentation to describe each of the 5 terms that results in a change in lapse rate with respect to time. There are points specified in each diagram where we can consider local lapse rate changes with respect to time. In term A, which is diabatic heating, we might consider the release of latent heat in a thunderstorm, with a maximum in diabatic heating occurring somewhere in the mid-troposphere. In that situation, lapse rates would decrease below the maximum in latent heat release and increase above the maximum. For term A, you might also consider heating or cooling of the ground through radiative processes, which generally contribute to a positive change in lapse rate during the daytime hours and a negative change in lapse rate at night. Term B is the horizontal advection of lapse rate, which we have already discussed. It turns out that lapse rates can simply advect around in the prevailing flow and yield local lapse rate changes at a given location. Term C is the vertical advection of lapse rate, which is analogous to term B. The vertical advection term is generally small and is somewhat complicated by parcel dynamics and the fact that the strong vertical stretching, which can occur in term E, becomes important when lapse rates are less than dry adiabatic, and can be especially large within stable layers and temperature inversions. So in term E in the schematic shown, we have an example of upward stretching within a stable layer, where vertical motion increases with height, which acts to steepen lapse rate. This can be important for weakening a capping inversion. And when the opposite is true, and downward motion increases with height, This will actually increase the capping inversion through subsidence. Downward stretching plays a big role in maintaining the capping inversion and indirectly maintains the EML by suppressing thunderstorm development in vicinity of mid-level anticyclones. So term E is very important in the long-range transport process of elevated mixed layers. Backtracking to term D, this is differential temperature advection by the ageostrophic wind. The ageostrophic advection can be large in secondary circulations associated with fronts and jets. If the secondary circulation is indirect, like the schematic shown, lapse rates would increase with time. If the ageostrophic circulation is thermally direct, meaning we have warm advection over cold advection, then lapse rates would decrease over time at a point marked by the dot. Using a procedure called scale analysis, we can come up with estimates for each of our 5 terms for synoptic scale flows away from jets, fronts, and other storm scale and mesoscale processes, namely thunderstorms. We did this in the Banakis and Extra paper, and we find that the horizontal advection term is an order of magnitude larger than any of the other terms. The diabatic heating term is quite small, as we would expect for clear, dry air in the mid-troposphere, where radiative processes are generally minimal. It's interesting to note, however, if we consider the latent heat released by lifting a parcel of air from the surface to 10 kilometers and converting 10 grams per kilogram of mixing ratio to liquid condensate, as a first-order approximation of what happens within a thunderstorm, we see that the diabatic heating term is now the dominant term by at least an order of magnitude. There is massive latent heat release within a thunderstorm due to the latent heat of condensation, and we know that thunderstorms will tend to move lapse rates towards moist adiabatic values as the air mass becomes worked over. So deep moist convection has the effect of quickly destroying the EML. So while the advection term is large, if we want an EML to survive from the Rockies all the way to the Northeast, we need to limit thunderstorm development en route along its trajectory, and that is typically difficult to do. In an observational study by Banakis and Exter, we had a hypothesis that significant severe weather is more likely in the presence of an EML because it establishes a thermodynamic environment that is reminiscent of what we see relatively frequently in the Great Plains. As a reminder, significant severe is defined by EF2 or greater intensity tornadoes, 2-inch or greater diameter hail, and wind gusts at or above 64 knots, which is hurricane strength. We use the severe plot software to narrow down days with significant severe weather reported in the Northeast from 1970 through 2006 and for the months of May 1st through October 1st. This was a quick way of identifying the bigger severe weather events and then backtracking to look at available soundings for the presence of an elevated mixed layer. It should be noted that this study wasn't an EML climatology per se, as anecdotally we know that some EMLs can pass without convection at all, and those days wouldn't be examined. Also, we should note that some wind damage produced by significant wind won't be included in our catalog of events if it occurred in the absence of a measured gust meeting the significant severe criteria. This is what the distribution of significant severe weather reports look like over the study region. Keep in mind that this study only goes through 2006. Most of the significant severe reports are focused from the Mohawk Valley of New York and southern New England and points to the south. There were 447 days in total and 929 significant severe reports. The next step in the study was to determine how many of these days were associated with an elevated mixed layer. For an EML to be defined, an observed sounding in the region had to have a lapse rate of at least 8 degrees C per kilometer over a depth of 200 millibars or more, and those lapse rates had to be what we'll call non-surface based. Also, the relative humidity in the layer must increase with height, and we ensured that the steep lapse rates are not associated with being in the vicinity of a cold core upper low. Lastly, the EML had to be traceable back to an elevated terrain source region, and we did that using the NOAA high-split model. The lapse rate criteria are somewhat arbitrary, but we arrived at this through trial and error and visualizing each sounding to see what would be reasonable and unambiguous. We believe that marginal or questionable EML events were eliminated from consideration based on these criteria. In doing this in our study, 34 EML events were found from 1970 through 2006, and we added 2 other known cases from before 1970 based on prior studies. So it turns out that EML events accounted for only 7.6% of all days with at least one significant severe report. This is relatively small, but note that these events accounted for 20.3% of all significant severe reports in the database and 35.9% of all significant hail reports. Therefore, EML days account for a disproportionately large portion of significant severe weather reports and especially significant hail reports in the Northeast, even if the number of times we get an EML event is only on the order of once or twice per convective season. So when they do happen, these EML days are nearly always big and important severe weather days. So what is different synoptically between a significant severe event with an EML and a significant severe event that doesn't include an EML? The North American Regional Reanalysis Data, or NAR, composite 700 millibar heights based on the 36 EML cases is shown on the left. The NAR 700 millibar height composite based on 413 non-EML cases we cataloged is shown on the right. Based on the height anomalies, note that the 700 millibar ridge builds more strongly northward across the Tennessee and Ohio valleys in the EML composite. The shortwave trough north of the ridge axis is of lower amplitude, but the implied mid-level geostrophic flow is stronger. There is also a deeper trough along the west coast of the United States, and more anticyclonic curvature to the flow across the central and northern plains into the upper Mississippi River Valley in the EML composite. Also, the flow aloft is more westerly in the EML composite towards time equals 0, which is the day of the severe event, while it becomes southwesterly in the non-EML significant severe cases in response to a deeper trough approaching from the Midwest and Great Lakes region. The top loops show the evolution of the 700 millibar height anomaly field from T-5 days up through the day after the significant severe occurs. The positive height anomaly associated with the building ridge over the Tennessee River Valley is strong in the EML composite. There is also a stronger negative height anomaly field along the west coast, which helps to eject the EML plume northeastward from the Intermountain West across the Great Plains. The non-EML significant severe composite is associated with a strong, higher amplitude 700 millibar trough axis, with a wave train of positive and negative height anomaly couplets. One can also see the digging nature of the 700 millibar trough across the north-central United States in the non-EML 700 millibar height anomaly loop. The pattern differences are also readily apparent at 500 millibars. On the left figure, a positive height anomaly associated with a stronger ridge axis is seen across the Ohio Valley in the EML composite, with a strong height anomaly gradient evident on the north side as a mean shortwave trough translates eastward across the northern Great Lakes. A negative anomaly is present along the west coast, a feature that doesn't appear in the non-EML composite where there are positive 500 millibar height anomalies across the Intermountain West. Also, the non-EML composite on the right features a stronger and more meridional upper trough and associated negative height anomaly. So the synoptic regimes are dramatically different. For EML cases, we are seeing the importance of the mid-level ridge and potential anticyclonic curvature prior to severe convection, helping to maintain the EML plume eastward. As one might expect, there are also stark differences in the 700 millibar temperature anomaly field. The EML plume, generally associated with very warm 700 millibar temperatures, produces an elongated positive temperature anomaly extending northeastward from the central Rockies as seen in the loop on the left. This is effectively a plume of relatively hot air near 700 millibars. The anomaly increases in magnitude eastward as the spatial location of very warm 700 millibar temperatures with the EML becomes less frequent to the east per climatology. The 700 millibar temperature anomaly field is clearly weaker in the non-EML composite and more in line with what we would expect with a deep large-scale trough approaching from the north-central United States. Here's a look at the mean daily 700 to 500 millibar lapse rates and associated lapse rate anomalies for the 36-case EML composite. These graphics are valid 48 hours prior to the first significant severe report. While differences in timing and spatial location of individual cases result in smoothing of the signal, anomalies on the order of plus 1 degree C per kilometer are apparent across the Central Plains and Midwest as the EML plume ejects from the Rockies. Note also the anticyclonic flow and shortwave ridging evident in the mean 700 millibar heights in the Midwest and upper Mississippi River Valley. At T-minus 24 hours, the steep lapse rate plume is advecting eastward in relatively fast mean 700 millibar flow, again with a slight anticyclonic curvature. The mean east-west 700 millibar ridge axis remains across the Tennessee Valley. There is also a hint of a shortwave trough in the mean in vicinity of Minnesota and Wisconsin, so there is generally an upstream trough that will be providing forcing for ascent the following day. At the 3-hour NAR time step closest to but preceding the first significant severe report, we see the steep lapse rates and positive lapse rate anomaly maximized across the upper Ohio River Valley into Pennsylvania and adjacent portions of the Northeast. The ridge axis in place across the Tennessee Valley maintains a fast flow regime, implying favorable deep layer shear for severe storms. Also, a mean trough is located across the eastern Great Lakes, providing forcing for ascent as it moves into the northeast. It is likely that what remains of the EML is being entrained into the trough along and ahead of the 700 millibar trough axis at this time step. To help emphasize the importance of subsidence and anticyclonic flow in maintaining the EML in the days preceding significant severe in the Northeast, this is a time series showing the mean backward trajectory pressure in millibars and vertical velocity in microbars per second for a 96-hour or 4-day period leading up to the time of the first severe report. The backward trajectory is started at a height of 3 kilometers above ground level at the time and location of the first significant severe report on each of the EML days. And these data are derived from the high split model itself. The first significant severe weather report is at hour 0 on the far right, and time goes backwards along the x-axis to the left. One thing we see is that there is downward motion in the mean for a period from T-minus 15 hours all the way back to roughly T-minus 72 hours. During this time, there is sinking parcel motion, which would suggest subsidence in the absence of much thunderstorm activity. So the synoptic regime is favoring maintenance of the EML through subsidence as the EML plume is getting advected generally eastward. It's not until the hours immediately preceding the significant severe that the sign of the vertical motion flips, and we know upward vertical motion as it undergoes synoptic ascent very late in the time series. This concludes part 1 of the EML presentation. Please refer to part 2 for the case study and a discussion of operational tools.